Okay, so what I'm going to talk about, our recent work using deep learning. And I've been working in this computer vision for a long time. So we used to do this classical computer vision. And in that, we used to solve a problem in modular fashion, and we will encode expert knowledge into constraints and convert constraint into objective function, and we optimize objective function. Now with the deep learning, it's very different. So it's end-to-end, so it's not necessarily modular, and there's real learning. And of course, it's motivated by human neural networks and requires label and enter data and need to define loss function and require massively parallel computation and uses simple stochastic gradient descent. We use very sophisticated, optimization methods. Excellent results. And so with that, I'm going to talk about very quickly about 10 different projects, and most of them I will just go through very quickly, but just give you insight that what kind of problems we are working on. So first problem is called human re-identification. And this is a paper we have in CPPR 18. So the idea here is that we want to retrieve an image of person from a large gallery, and there's a query image, and then there is a gallery or reference images, and these images can be captured by different cameras. And so it's kind of a cross-camera data association problem. So this is one famous data set, CUHK from Hong Kong. So there are about 1,360 identities captured by 6 cameras. And this is more statistics about that, training, validation, and so on. So the idea is that given an image like this, we want to find out top 10 matches from the reference images, and we want to rank them. So here, we have ranked 1 to 10. So green one are correct, red one are wrong. So the challenges are that, these images can look different due to elimination condition. There can be, person wearing umbrella, so you're not able to see the body parts. There can be, different posture of a person, background clutter, occlusion. As you see here, this person is being occluded by a tree. So simple way to do this is what is called person classification network. So we have image of one person, and we go through this DNN, deep neural network, and we want to classify that that person's image are classified as a person 1. Then we'll have example person 2, person 3, and so on. So it's like a simple image class, very similar to like your ImageNet problem you have learned in the 5415. So once it's trained, so then we will use these features which are learned for each different person, and we'll just do matching. So now our approach is that we want to use a semantic parsing, a semantic segmentation of person, okay? And then we want to actually train on multiple data set. And then this is our approach, which we call human semantic parsing for person re-identification. So this was a network. So it has 2 parts. So first is that we will take an image and resize and with the inception features like this, do the global average pooling, we'll get this feature vector 2048 dimension. Then we have another branch where again we compute inception features, and then we will actually do semantic segmentation. Okay, so semantic segmentation, these which are shown here, then we will get these features and do the weighted sums. And now we will have these features of the foreground, head, upper body, lower body, shoes. And we are going to kind of one feature vector of foreground, and then we'll combine these body parts in another feature vector. So then we will have basically 3 feature vector: global feature vector, the top branch, foreground representation, and the body part representation, and we'll concatenate. And then that's the feature vector we will use that for a query and go through the reference and match it with every reference and find out the best match. So this works pretty well. So this is the query. And if you just use the inception features, then you'll get a lot of wrong one, red one or long. Now, when we use our method, we get all of them correct. As you see, this is difficult because this is the person and, these are the matches. Here is also a pretty difficult case, and these are the matches with only inception feature. But when we use the semantic segmentation, we get all correct. And another example, again, very complex. So some mistakes here. So here also we have a couple of mistakes in our method. And then this is other example, and we get most of them correct. So this works well, and these were the other methods. Whenever you write a paper, you need to compare with other methods. And this is simplest inception v3, and this is at the end our all of things we do. This is our method. So now this is a very active area of the research, and we had a paper in 2018. We have another paper in 2019, which does even better. And so as you see that we talked about this simple classification network, and but there are many different ways to actually learn these features. So this is one simple one. Other is called verification network or SAMIS network. Okay. Now SAMIS network, the idea is that we take two images and we want to determine if they are similar or dissimilar. So that way also we can learn features. Another way is called triplet loss based network. So here the idea is we have positive, then we have query and one negative. So we want to learn the features so that positive comes close to the query and negative pushed away, because we want to get the better features for the positive or anchor. Then actually there's a quadruplet loss, where instead of 3, we have 4. We have the positive example, then query, then we have 2 negatives. Same idea that we want to learn feature so that this query become close to positive and negatives are pushed away. And you don't have to limit to the 3, 4, or 2. You can have any number of these images. So that's called diffusion network. And so we'll have lots of these, and we'll make the graph. We'll connect each of the image to all other ones, and then we will kind of cluster. Say this is our probe or query. We want to cluster similar images to this one, and then separate them. And that's the way we will learn the features. So this is our query, and then these are the other images, and then we want to make a graph, and then these are all images of same person, and these are other one, and that's the way we want to learn those. So we did that, and that actually works pretty well. So this is about 95. So that was one problem. Now second problem is tracking, multiple object tracking.
Excuse me, sir.
Yes, sir.
Yeah, there's a doubt, like in the person classification network, it was given like there are like 5% or n number of persons, and the network was giving the probability of which person it is. So if I have a huge gallery, there can be any number of persons in that. Then how do I fix the size of my output layer? Like I don't know how many persons can be in it.
Yeah, so because this is during training, so during training you will know how many people are there, as I showed you the slide. In the first one, say Hong Kong data set. So we know how many people are there. So therefore you can do that, right? So once you are done with the training, then you don't have to know people. Say suppose here, there are 1160 people. So that's what you will have, 1160 people. But once you are once you are learned, then you just get the features.
Yeah, got it. Thank you, sir.
So so let's go back to the now tracking. And so the tracking is also a very hard problem. And tracking, what we are interested in is like this. So we are given a video, we want to detect people and we want to track them from frame to frame. It's very, very useful problem. And we have been working on this for a long time. Now, typical formulation tracking is that we detect people first, and then we detect people in every frame, then we associate these detection from frame to frame, and we get the tracks. And this is called detection, this is called data association. Inputs the video, outputs the tracks, okay? Now, the data association has these steps that we want to extract features, and using features, we will come up with what's called affinity matrix. And the affinity matrix is that if we have 5 people in frame 1, 5 people in frame 2, then we want to find out, given this person in frame 1, how similar it is to person 1 in frame 2, person 2 in frame 2, and so on. So once we have affinity matrix, then we can actually do optimization and get the tracks, solve data association problem. So here's an example. So we have these frames and we have these different detection. So we will do these correspondences. Well, this yellow guy can match with this or this one. There are 3 possibilities. Similarly, this green guy can match with all these 3. So we want to come up with how much affinity this has based on the features to this one. Of course, this is the same person. Compare this one, but computer won't know, and that's called affinity matrix. And now with that, we can use frame by frame, or you can use multiple frames. So this is called bipartite matching, and this is called k-partite matching. Now what we used to do all time, that we will have separate step for feature extraction, separate step for affinity matrix computation, then we will do the optimization. Now with a deep learning, we can actually learn these compact features of object, and at the same time, the affinity matrix. So we have this network called deep affinity network, and that will learn the compact features of objects, and it will perform the exhaustive pairing or permutation and will account for multiple objects appearing, disappearing. So this is a network. So this is part is feature extractor, and this part is the affinity estimator. So in detail, we have this feature extractor, the way it works. So let's say we have this one person we already detected. So detections are given. So we will take that person and compute these features. This is from VGG network you have learned in the computer vision course. And so it has 256 channels. In another layer, it has 512 channels and so on, different resolution. So we look at these three layers of VGG, and then we will do kind of feature dimension reduction. From 256, we'll get 60. From 512, we'll do 80, and so on. And then we will take these from each of these, because this is a whole image. There are different people. Green is one person, red is another person, blue is another person. So center of the green person will get a feature vector, which is shown here. Then center of red person will get feature vector, all these, this is shown here. So we'll get 250 dimensional feature vector. Similarly, from here, we will get 80 dimensional feature vector, and so on. So we'll flat these up, and we'll do the same thing for the second frame, same way. And then we have these additional layers. We introduce 5 layers, and we'll have also 512 features here. We'll do reduction to 80 and all this thing, and then flatten those. So we'll get all those and then come up with this long feature. So this green one from all these layers, it'll become 520. And same way from the second frame, 520. So we'll line this up and we'll get this cube. And then the way we are going to get a cube, so we'll take the green one from first frame and try to match it with green one, with the red one, blue one, all these, and that's what we will have here. and we'll take the red one again, we'll match like that. So given this Q, we'll have this compression network, additional feature, layers, and then we will come up with the affinity matrix. So if we have NM objects in frame 1, NM objects in frame 2 will become NM by NM matrix. So they tell you the green object, how similar it is with itself, which will be high, but when the second one, third one, fourth one, that's the affinity matrix. Okay, so now it can happen that the object can disappear, our new object can enter. So that's why we will introduce one additional column and additional row, and so we'll have actually 3 of these matrices, and we will have losses for these, and we will minimize and we'll compute. So I'm going to skip those because I don't have time there. So so here is the kind of qualitative explanation. So let's say we have frame 1 and frame 30. So these are the objects, the people, similar, and we are showing these people here. Now, as you see that, like, this person is not here, okay, and this one, there's a new person appear, which is not here. So therefore, we look at what's the maximum number of people can appear. So let's say 5. So we will have this, 5 by 5 matrix. And even though we have only 1, 2, 3, 4, but we will introduce this this one, which is X, which will be like a dummy row, and to take care of that. Similarly, in this one, so we have this new person enter, as you see, this one, and so we'll have that. So this is essentially the affinity matrix for the ground truth, and we are going to use that to learn. So this works pretty well. These are the tracking results. Very nice work. We can track these in crowd people. This is the cards. And now we can extend this to actually, that was 2D tracking, so it's regular camera. We can extend that to 3D tracking, which is the LiDAR, and that's being used in self-driving cars, as you may have heard. So LiDAR is like this. So LiDAR gives you these point clouds. So there are each points, and each point has 3D location, X, Y, Z. So we want to take this kind of data and track people. So instead of 2D. So there's another example here, which we are showing. This is the outdoor. So actually we can use the same approach, extend to 3D. So again, we have this point cloud in T-1, point cloud in T, and we get the detections and then compute these features as we did before and get this cube, and these are the matrices, and then we can minimize the loss. And it works pretty well, So this is the results for the kitty data set. And then this is for pedestrian. It works pretty well. Actually, this got award last year in CVPR workshop. Okay, so now the other thing is that while we say, so far we assume we are giving detection and we want to compute affinity matrix. Now, how about we can actually do end-to-end? We don't assume detections are given. We can do detection affinity matrix together. So we have another paper in ECCV last year, 2020, and which actually does that. So input is the images, not the detection, then we can get tracks. And that works pretty well. These are some results, vehicle tracking, and these are some results. Another data set, this actually synthetic data set we created. So now the next thing is these cameras were fixed cameras. These are called like, physical surveillance or, fixed camera. Now they are, as you know, they are drones. So drones are being used for agriculture, entertainment, military, surveillance, sports, and so on, and the wars. So now the difference in drone video is that the camera is moving because drone is moving. These cameras previously, what I showed you, are fixed. So that's another complexity. So we have this paper in CPR 18. So we look at this kind of video. So this is called wide area video analytics, wide area motion imagery, WAMI. So this is actually a video in the Ohio State campus. So you can see there is a stadium, football stadium somewhere around here. So this actually was captured 6 camera, that's called wide area like this. So given this kind of video, so our problem is to detect these vehicles. And these vehicles are very, very small. As you see, they are basically dots. So it's pretty challenging problem. And these are different cameras. You see the brightness changes. It's different than this one. So we solved this problem. So we are looking at, say, we want to detect the vehicle in center frame. So we look at the 5 frames. So we compute, you have these 2D convolution, and then we add them up, and we have this binary segmentation of each of the vehicle. And these were the convolutions, and works pretty well. As you see that, the greens are the ground truths, and red circles are what we can detect. So most of the time we are able to detect those. And this is kind of performance, we are pretty good, very nice compared to these other methods. Now, we had a paper in last year's CVPR, we call it dogfight. So there we are looking at the video of drones taken by drones. So there's this, 2 drones basically. We want to capture how drone is moving by a video taken from another drone. So that's why we call dogfight. So we have this approach where first we take each image and get potential detection. Then we actually get these detections in different frames and track them. And then we use motion information to actually improve the detection. So these are the results. So as you see that this works pretty well, and it's a very complicated problem. So ground truth is green, and the red one is the actual detection. So one thing I want to mention that for all these papers, we have, paper, website, the presentation, project page. So if you are interested more, learn, then please, feel free. We have a YouTube video for each of these, and you can actually watch those. Okay, so now another problem we are interested in detecting anomaly. We had this paper in CVPR 18, and this is the video for that. You can watch in video, about 15 minutes video on YouTube. So let's say, as you know, there are so many cameras, this is 2-3 years old. There were, 30 million cameras just in US. So, and nobody is watching them. So the question is, can we automate that? So in particular, we are interested in the anomaly, the crime data, like abuse, arson, burglary, assault, and so on. So we collected a data set, which is very popular, and we solved the problem. So now it's not easy to go through these videos and annotate where it's normal, where it's abnormal. So we wanted to avoid these annotating clips, but we wanted to have the weekly supervised. When you have annotation, then it's supervised, fully supervised. So we use this multiple instant ranking and weekly supervised. So we have a video and we know there's an anomaly, but we don't know where it is. and we have another video, we know there's no anomaly. So that's the idea. So what we did, we wanted learn this ranking function such that when there's anomaly, this is higher than when there's no anomaly. So this can be written like this, because we have a video which has batches, which is a batch which has several little clips. So we want to say like the maximum of those should be greater than maximum of that. So this is last function, and actually it works pretty well. So here's example. So this is the function which you learn. So whenever there's an explosion, then this function will be very high, as you see here, and then it'll become low. So here's another example, road accident, again high, shooting high, and this of course is normal video. We are playing it fast, but there's nothing, abnormal here. So then the other thing we want to do is, again, suppose this is a YouTube presentation, if you want to watch, is to take actions in the video, what kind of action it is. And so we had this method, which is similar to FastStart CNN, but this is for video. So we have an input video, we divide in clips, and each clip we get the action to proposals here, proposal here, then we link them, so we get a full proposal, and then we do the pooling, and we actually recognize actions and localize, and we get very good results. We see here, we can recognize action, say horse riding, but say where it is horse riding. We can put a window, golfing, running, diving, more examples, picking, clapping, and so on. So now most of the work you have learned in 5415, and so far what I have talked about is using CNNs, right? The convolutional neural network. Now that's kind of gold standard, and it's achieve strong performance. It needs large amount of label data, and deeper architecture and all this thing. And in the video, it's just 3D CNN as compared to 2D CNN in the images. Now there's an issue with CNN that CNN don't explicitly model entities. What that means that because you have an image, you just do max pooling and loss, you basically lose the spatial information. So due to that, the problem is, like, if you look at a face image on the left, so CNN will say, yeah, there's a face, you can train it. But if you give an image on the right, it will also say it's a face, even though it's not a face, because it's spatially not consistent. So that's a problem. So there was nice idea of capsule network, again proposed by Hinton, who's like a father of the deep learning. So capsule network, what it does, it adds an extra structure to model the entities. So it's actually a group of neurons, not just, you get a vector value as compared to scalar. And there is this what is called routing by agreement. So there's a whole part to whole relationship. And this is inspired by inverse graphics. And so as you know, in computer graphics, you must have taken a course. So let's say we want to render a rectangle at this location, this angle, triangle in this location, this angle. So we can do that rendering. We get an image like that. Now that's computer graphics. Now inverse graphics is we are given an image, we want to invert that. We want basically come up with that there's a triangle with this location, this orientation, there's rectangle, this location, this orientation. So that was the inspiration by Hinton to do that for images. So capsules, essentially is a 4x4 pose matrix and activation neuron. And so capsule in lower levels will vote on capsule in higher levels. And so there's a parts prediction of the whole. And then we group the votes, and the way to do is what's called routing by agreement. So this is the main thing in capsule, and it's pretty interesting concept, but it's not that easy to understand. So that's why capsule is not that popular compared to CNN. So it basically transforms low-level capsule to higher-level capsules. And so as I showed you this example, and this problem we saw on the right side, this capsule will solve that. And so because it's looking at the part to whole relationship, so suppose this part, left eye will say the center of the face is here, it will point that. The right eye will point also here. Then in nose and other parts will point as the center of the face, based on the parts. So part to whole relationship. Now, if you give this image, the capsule, so there's an agreement, okay? So there's an agreement that while these parts agree on the same location, the center of face, and so this is a face. But in this case, now this eye will vote like this, and which was this eye here, and this will go vote like this, as you see here. And similarly, the other parts, there's no agreement, so they're voting. So that's a main inspiration, which is, I think, very important. So using that, we have done this work. We have used this capsule in video, which we have generalized the capsules to 3D. This was the first time anybody did that. So we have very nice work by my student Kevin, who graduated last semester, and he has his PhD defense is available here. It's a very nice talk. You should listen. So you can solve this problem called, the video object segmentation. So you're given a video, and you are given a first frame, and you are given a segmentation the first frame, say of this deer. So you want to segment this deer in all the frames in the video. So we have video encoder, frame encoder, we use these capsules, video capsule, frame capsule, and we combine route and we get this output. So we get excellent results. So these are the results using method. This, very nice. It's I never thought we could get these kind of results, say 5 years ago. And this is using capsules, single object. We have multiple objects, as you see. Again, we can segment these. There are these different sheeps, different airplanes, cars, all these animals. So then we can use also capsule on the text-backed video segmentation. So here, the idea is that we are given the sentence and the video instead of the frame segmentation in the previous work. We want to do the segmentation. So we are given the video, we do the capsules, and we are given the sentence also, woman in a green top standing on the left. So we encode text, we encode video, and we get these capsules and combine them, and we get segmentation. So again, we can do pretty well. So this sentence, the person is walking backwards while being followed by a dog. Given the video, we can actually segment this person. Then another sentence, a black dog is crawling, we can segment like that. And then baby crawling in the corridor, we can do that. The dog on the right is crawling, okay, we can do that. And dog on the left is crawling, we can do that. So this is a video. So you send a baby in the white is climbing the stairs. So this is a ground truth. And this, if you use keyframe, this is what we get. Bounding box is what we get. These are two sentences: baby sitting on the ground, pink ball rolling. Again, very good results. So the next thing I want to talk about is another problem, which is very different. which is called ground to aerial image matching. And this we can use also in geolocalization. So the idea is, we call this problem actually, where am I? So let's say you are lost and your GPS doesn't work in your cell phone and you don't know where you are. So that's why it's where am I? So let's say you take an image and you want to find out what's your GPS location. And so we can do that using this method, and we'll find out the GPS location is this one, longitude, latitude. And this happens to be taken image in Pittsburgh, Pennsylvania. So, so now what this paper solves problem is a cross-view geolocalization. So we have say ground view, this is a ground panorama, and we have the aerial view of the same area. So we want to automatically determine that this image matches with which one now. It's a pretty complex problem, even for humans. Okay, so what we do, we take the ground image and we synthesize a corresponding aerial image using gain. Okay, so then we can find out that, well, this matches very well with this compared to this one. So that's what cross view matching is. So so we do the cross view image synthesis. After that, then we learn the joint features, and then we fuse the features. So this is the ground panorama, and then we apply edge detection, so the edge map, and then we want to get aerial image corresponding to that. So, and also semantic segmentation. So we have this generator, which will take this and generate this. And so now let's say we have that, and this we will call A prime, synthesize aerial view. A is aerial and G is ground, and prime is synthesize. So we take the synthesized aerial, and we also have the ground image, and we have real aerial corresponding to that. So we have these three images. So we do the encoding, we get these features, and then we call this ground features, synthesized aerial features, and aerial features. Then we concatenate these two, and we combine in one fully connected layer, we get this FG star, which is like ground features. Then we have this also FA star, which are the features for the aerial. And so we want to say that these features should be the same, very similar, because the same area, they should match. And so that's the way we learn these features, and this works pretty well. So say this is a ground query, and we find out that from the aerial, this matches with this, which is even hard for humans. And these are top 5 matches. And actually, this is within 0 meter, we can geolocalize. This is the exact match. This one is another match. This is within 2 meters, and so on. So that is the cross-view matching and geolocalization. Now, we had paper last year in ICCV where we extended this to video. So the idea is that we are given, instead of image, we are given a video clip, and we want to estimate GPS location of each frame in the video, and then we want to smooth the estimated trajectory. So like video like this is a video from the San Francisco area, I think. So this is a trajectory, and these are the different frames. And so we want to be able to do that. So this is, which in a way uses transformer, and which we are going to focus on in this course. So we have these query frames, so end frames, and we have these gallery images, which are the street view images. So we do the encoding, and we do the attentions, temporal attention, and then here the self attention, and max pooling, and we have these losses, and we can train this, and it works pretty well. So red is the estimated trajectory, and green is the ground truth, and you see we can do very well here. The more examples. So the main thing is to look at how much errors we have in geolocalization. So there are these San Francisco, Bay Area, Berkeley, and New York. And in this one, we can do up to within 128 meters, which is pretty good using this method. So that was the geolocalization. Again, so I'm going very quickly just to give you a sense. I don't have time to go through in detail, but if you're interested in any one of those, so you can just look at the paper, look at the YouTube video, and so on. So this is also a very nice, good paper we call Rescue Net. So it's we want to assess the damage from satellite imagery. So there's this data set called XPD data set. This is for the humanitarian aid and disaster relief. So there are these 19 disaster events like floods, volcanic eruption, earthquakes, hurricanes, and they have collected these data images, satellite images, and there are 4 classes damage labels for each building. So we had a method to do that automatically. So your image before the damage and image after the damage, we compute some features, pre-image and post-image, concatenate, and we want to do segmentation. And we have this building detection because we have annotation, and we want to say location-aware damage classification. And then we actually subtract these features, and also we look at the chain detection. And it works pretty well. So this is the ground truth. So here you see blue is I cannot see here. Green is undamaged, red is complete damage, and pink is building with major damage, orange building with minor damage. These are ground truths. Each pixel has label. And this is our results. So it's pretty close, which was very good. Okay, so the next one is the paper we had last year in ICCV. So this is on the face image retrieval. So let's say, you're given a query image like this, you want to find out this guy in the big data set. So these are similar faces, and you can do that. It's, kind of solve problem. But what we want to do, we want to give more flexibility to user, that user can emphasize or change attributes of the person. So simultaneously adjust the facial attributes, assign preference to different attributes. So we have this method. I'm going to skip that, but let me show you what we can do. So let's say this is a query. So these are the base matches of this guy. Now what we want to do, we want to get only those are bald, So I want to emphasize the baldness attribute, and this is what we retrieve. So as you see, it's kind of bald. Then we want to add to that, we want to remove smiling faces. All these smiling, same guy, but now we remove that. So again, another example, this is a query, and these are the matches for this lady. And here we want to find this person's pictures matches with bangs. So as you see, you have more bangs here. And then we want to say add black hair. So all are black hair, not blonde hair. Then we want to say eyeglasses. So again, this one. So that's we can do. And the last paper is, more on reasoning. And so the idea is that, let's say there's this area what is called visual question answering. So we are going to image, and the question is, are the black horses to the right of the vehicle on the road? Okay, that's the question, and the answer is yes. But we want to do more than that. We want to actually ground the question, and we want to say the reason we say yes is because we localize the horses, localize the vehicle, and that's true. It's on the right. Another example, there's a cube that is in front of blue rubber cylinder. Is it same color as metal sphere? The answer is false, but we can say reason was found based on this localization. So that's what we have. And so talk about very quickly 10 different projects which we have been working on. Person identification, multiple object tracking, drone video analytics, anomaly detection, action localization, video object segmentation, building damage assessment, face retrieval, geospatial localization, grounded visual question answering. So as I said that, this is the classical computer vision, this is the deep learning. So one thing is that deep learning requires label or annotated data, which is a big problem. So now we have started working on to resolve that. And so what I've been talking about so far is called supervised learning, as you have learned also in 5415. So we have label data. So we need to construct large label data. It's expensive, time consuming. There are actually companies which are doing this, and they're making millions of dollars. They employ lots of human cheap labor, and they annotate. So what we want to do, we want to learn with less labels. And there is this research in 3 directions. One is called semi-supervised learning, other is called few-shot learning, and third is called self-supervised learning. So semi-supervised learning, the idea is that we have small amount of data which is labeled, and large amount of data is not labeled. So we had a nice paper last year, which kind of solves this problem. And the idea is very simple. So let's say we take the label data, small amount of data, we train the network. Okay, so this is our trained network on the label. Then we take the unlabeled data, we run through this network we train, and we get these labels. Okay, now we want to look at, say, well, it tells us this is a label for this, this label for this, but we want to look at also how certain we are. And using this uncertainty, we kind of select, we don't use all of these. And then we select these, which are certain. We add these to the label data, we train this again. So we go through this cycle. And these labels we assign to the unlabeled data is called pseudo label, because we didn't have labels, so we just assign based on this network we train on small label data. And this works pretty well. So here we just label 20% of the data. We can get pretty good results. 50% of the data we get this, and same way here. So that's one dominating approach, is semi-supervised learning, which require less labels. Second is we had another paper in CVPR last year, few shot. So where we have only few shot or label, rest of them are not labeled at all. So there's another area. There are lots of good papers there. So that's few shot learning. And then the last one is self-supervised learning, where we actually don't need any label. It's all unlabeled data. And so it applied a pretext task and fine tunes on downstream. So we had a nice paper on the archive on that. Okay, so now, so this is about labels. Now, other problem is that, this deep learning requires massively parallel computation, and that's a big problem. So, for example, this article I showed you before, this is becoming unsustainable. And for example, you might have heard about, Go, this DeepMind system Go, which won the, competition from this guy in Korea. It cost 35 million to do that. And you have heard about GPT-3, OpenAI, it's got about 4 million to train. So that's the problem that, now if you want to train ImageNet, improve the performance just by 5%, that will require a lot of resources and energy. So it will require equivalent to carbon dioxide generated by New York City in 1 month, just to improve 5%. So that's a one concern, okay? So that's why people are looking into different way of computing now these GPU from NVIDIA. So that's the end. So thank you for listening. So I'll end here, and